Hi, and welcome back. The stepper motor is considered as a specialty type of motor used when high precision positioning and high holding torque is required. You find them in applications like disk drives, printers, industrial machine tools, scanners, and camera lenses, to name a few. You may remember from the lecture on the servo motor that servo motors are also good for precision positioning. This is achieved by a feedback mechanism embedded in the servo motor's chassis. Servo motors have limited rotational capacity, usually not more than 180 degrees. In a stepper motor, the shaft moves in steps or increments, and hence the name. In the images here, taken from the stepper motor Wikipedia article, you can see that an arrangement of 4 electromagnets is positioned around an iron-toothed rotor. In the first image, the coil of the first electromagnet is energized, and as a result, the teeth of the rotor are attracted and aligned appropriately. In the second image, the first electromagnet is de-energized, and the second is energized. As a result, the rotor advances by 1 step so that its teeth are again appropriately aligned with the new electromagnetic force. The same process repeats in images 3 and 4. As you can see, a stepper motor's rotation can be controlled precisely by controlling the pattern by which the electromagnets are energized. As long as externally applied torque does not force the shaft to skip or miss any steps, by perhaps a heavy load that the stepper motor can't move, the motor controller will always be able to maintain accurate positioning information. Unlike servo motors, stepper motors have no angle limit. So, in principle, the basic physics and construction of the stepper motor are straightforward. Before continuing with this lecture's demos, I'd like to discuss some more interesting details. There are several kinds of stepper motors, but in most cases you and I will come across we will be using the so-called two-phase unipolar or bipolar motors. In a unipolar two-phase motor, you get 2 coils, 1 for each phase, and each coil is split in the middle with a common wire, like in the image here. In most cases, the wire that is used to split each coil is common between the 2 coils. You can identify two-phase unipolar stepper motors by the total number of wires that come out of it. They have 5 wires, 2 for each coil, plus 1 common from the middle split of each coil. The common wire is used to make it easy to reverse the rotation of the shaft without changing the direction of the current. Because we will be using a motor controller in our demos, we are not concerned about this feature of the unipolar two-phase motor. We will actually be using it as if it was a bipolar motor, ignoring the 5th wire. In bipolar motors, you still have a coil or winding per phase without a common wire. You can figure out if you have a two-phase bipolar motor by counting the wires that come out of it. If you have 4 wires, then you have a two-phase bipolar stepper motor. There are also stepper motors with more than 2 phases. The more phases there are, the more power and precision these motors can deliver. The control then becomes more complicated and the cost much higher. Back in two-phase stepper motors, it is worth knowing that you can find them as geared or ungeared assemblies. In a geared servo motor, like the one in this image, the package contains gears that drive the motor shaft so that its rotational speed is reduced. This results in a higher torque with less power and less external rotational speed. You can determine if you have a geared stepper motor by checking the location of the shaft. If it is displaced from the middle of the assembly, then you can be confident that you have a geared motor. The one in this picture is very popular, and you can find it on eBay for around $3 with its controller board. I'll be showing you how to use this motor in one of the demos that follow. Ungeared motors usually come at higher voltage ratings, at least 12 volts. Here's the one that I got from eBay for $12, and I will also demonstrate it in this lecture. You may be able to read the label stuck on the package. It reads 12V 48 step 7.5 deg for degrees. That means that the input voltage for each coil is 12 volts, so that you must use a motor driver to supply the power. Each 360-degree full rotation is achieved with 48 steps, and each step rotates the shaft by 7.5 degrees. You can also do a quick calculation and see that 360 divided by 48 is 7.5 degrees. Therefore, 7.5 is a minimum accuracy for this motor. If you need something more accurate than this, then you can use a higher phase motor or a geared motor. Stepper motors are controlled by well-timed pulses generated by a microcontroller that can energize the electromagnets. The Arduino can't provide enough power, so external driver circuits are used. In the demos for this lecture, I will be using the H-bridge driver chip L298N motor driver breakout, the exact same one used in the DC motor lecture. To jog your memory, I'll remind you that a DC motor has a single coil, and once power is applied to it, the motor spins. The breakout has two outputs, so it can control either two single-phase DC motors or one two-phase stepper motor. I am planning to create a supplemental demo for this lecture where I will use the very popular EasyDriver 4.8 board. It is a more expensive driver compared to the L298 based ones, but provides more controlling power features. I will be connecting the EasyDriver to a 12-volt two-phase 1.8 degree stepper motor that you'll find in industrial CNC or computer numerical control machines called NEMA 17. CNC machines are used to create mechanical parts by milling a material like wood or aluminium.